Welcome everyone. This is the second video on properties of matrix operations, and I call this the part two, and then this is about matrix multiplication. So let's go over the theorem and the properties first, and then we're going to try to prove the one of them. So well, it says if A and B and C are matrix with sizes which matrix multiplication is defined, that means they're okay to be multiplied, the sizes, then we can have the following properties. So property number one is the associative property of multiplication. It works for matrices. A times parenthesis BC is the same thing as AB inside the parenthesis times C. Next is the distributive property. A times B plus C is the same thing as AB plus AC. We again have the distributive property here. A plus B times C is AC plus BC. And we have the associative property of scalar multiplication. C times AB can be written as CA times B and can be written as A times CB. These are all the same. And please don't forget, these are all matrices. So if you multiply them, you do get a matrix. On each side, the left side is a matrix and the right side is a matrix. I put a note here for you. AB is not the same thing as BA. So matrix multiplication is not commutative. And you can try that, especially if the size are different. Try that and you'll see it's not commutative. So you can't say AB equals to BA because they're not equal. Next, to prove these are all theorems, so you can prove them. There's several ways to do that, but I'll introduce you to one way, and I think it's pretty simple and straightforward. When you want to prove those properties, use the size analysis, part one of the proof, and use the entry analysis, part two of the proof. And if they both work, then that means the identity or the equation is true. So let's do an example. It says given A is an M by P matrix and B is a P by N matrix and C is a P by N matrix. Sometimes in the problem, they are going to give you the sizes. If they don't, then you have to come up with the sizes because you know they have to be defined with multiplication. Then it says prove, this is property number two. A times B plus C equals to AB plus AC. And again, don't forget this is a matrix and that equals to another matrix on the right side. Now I did start the proof by size analysis. So I called LS to be the left side and RS to be the right side. So then I numbered them. So LS, number one, the size of the left side, A is MP, and B is P by N, and C is P by N. So A plus C, of course, is going to be P by N. If we multiply A times that matrix, the product will be a M by N matrix. Then the right side, A is M by P and B is P by N. If I multiply them, I get an M by N matrix. Same thing with C, A is M by P and C is P by N. If I multiply them, I get an M by N matrix. If I add those two matrices, the answer will be an M by N matrix. So the size of the left side is the same as the size of the right side. And I put A times B plus C and AB plus BC have the same size. So part one of the proof is done. So now we're going to go to part two, which is the entry analysis. And I put the ijth entry. What you want to show is the ijth entry of the left side is the same as ijth entry of the right side. So let's go ahead and do this. I called the ith row of A is, again, if you write A as expanded form, you're going to get this big matrix, but you can write the iterate is AI1, AI2 up to AIP because it's an M by P matrix. And that's how you can write the iterate. You don't have to write the entire matrix. And I wrote the jth column of B plus C matrix. The jth column is going to be, again, these are all J's. If you write the entire matrix is going to be very big, the jth column will do it. So it's a A1J plus C, 1J, and so on. And you start at C, PJ, because that's a P by N matrix. And why did I put ith row and jth column? Because we're multiplying them. So we're going to multiply this row by that column. So the ijth entry of A times B plus C is just sum of A ik times B kj plus C kj. One more time. This is the general form of writing the entry of the product of a matrix. And don't forget, when you write that again, it's when you say I, J, that means this is going to be I, and these are J's, and those numbers, the K changes and K goes from 1 to P. And what is P? P is just that number. So now when it's summation, you can, again, these are just numbers, so you can distribute and you can write the sum like that. And I is a number between 1 to M, and J is a number between 1 and N. I call that number 1. The ijth entry of AB plus AC, you can write that as the AB. When you write it, then you know, again, from the summation notation is AIKB KJ, and the sum going K going from 1 to P. Same thing. P is that number, and that's plus, and then AC can be written the same thing. ijth entry, IJ, you put it here, you put your K, and it goes from 1 to P. And if you have two sum, you can just write that as one sum, and that's what you get. So, and I call that number 2. So this is the ijth entry of the left side, and this is the ijth entry of the right side. We notice that they're exactly the same. So I put 1 equals to 2, and I wrote it. ijth entry of A times B plus C is the same thing as ijth entry of AB plus AC. And again, I is a number between 1 to M, and J is a number between 1 to M. So both the size analysis and entry analysis are proven. So therefore, well, I just put the QED right there. So size analysis and entry analysis is one of the best ways to prove the properties of matrix multiplication. Let's talk about identity matrix. So identity matrix is the way you write identity matrix is I sub n, and I sub n, the compact form is IAJ, and it's always an n by n square matrix. And that's the entries are 0 if I is not equal to j, and the entries are 1 if I equals to j. That means the diagonal entries. Examples of that, if I2 is, you can write it like that, 1 0 0 1, and I3 you can write it like that. Basically, when you put all ones in the diagonal and zeros in the lower and upper triangles. Now, what is the identity matrix? If you multiply the identity matrix by any matrix, you're going to get that matrix. That's why we call it the identity. And vice versa, A sub m n times in is going to give you A sub mn, the same matrix. Little definition here. You can take a matrix and raise it to any power you want. K is a positive integer. So A to the K is A times A times A. You can multiply them, and they're ways we can do this fast, which we're going to learn in the future lectures. And it has to be a square matrix. So that's the note I put. I think that's it for this lecture. Please watch it 2-3 times, especially the proof, and try the other properties to prove it yourself. Thank you, and I'll see you in the next video.